CHED Talks. CHED stands for Cheesehead Engineering Discussions. Today we have a very special guest with us. His name is Petrie, and he's here to talk to you guys about what he does at his job and what inspired him to pursue engineering.
Okay, thanks for everybody coming to this mandatory meeting. I'm Bruce. I've been with Dominion about 10 years, but been in the energy industry about 25 years. Dominion, of course, if you don't know, they're the company that provides the electricity to your house. Really interesting business. I mean, I've been doing this stuff for a long time. When you look over the past 10, 20 years, everybody's got a cell phone. This one's a little old, but between Blackberries, TVs, cell phones, it all is driven by power. And you got to have enough power for every consumer to get everything that you need at your house or at your business. Businesses like this, whether it's a Walmart, a business like this, your house, or great big industries like paper companies, paper mills, where they use, where their power bill runs into the millions of dollars per year. But I've been at Dominion 10 years, like I said. What I did was I dug up, if you went home and looked at your parents' power bill, if you look up what's on that power bill, it's broken up into 4 basic components. If you forget about taxes, I'm not a tax expert, but if you look at your basic power bill, there's 4 components. There's distribution. That's the wires in your neighborhood going into your house. There's ESS, or energy supply. The energy supply portion of the bill, and that's broken up into 3 components: generation, transmission, and fuel. And what I do, my job focuses on the last part. It's the fuel part. What we do, and on my monthly bill, the total bill might be about $104, something like that. That $30 a month that I pay for fuel, what does that pay for? It pays for the uranium that's in the nuclear plants. It pays for coal that's burned at the coal-fired plants. It pays for oil, natural gas, and purchased power that we buy from our neighbors. So when I pay my $30 every month, it's my little share of the billions of dollars that Dominion pays for fuel every year. Let's see. So, I mean, the thing that I think is kind of interesting when you look at the 4 different components, and I don't even know very much about the other parts of the business. I mean, I know what they do, but I've never been a distribution engineer. I've never had to design a substation or anything like that. But I know a lot about the generation side of the business, where the fuel comes from, where it's, how it gets to the power plants, whether it's by rail, like coal comes by rail, or gas pipelines. They find the gas either down in the Gulf of Mexico, or they find the gas up in these wells now in Pennsylvania and West Virginia. They're finding natural gas all over the place, and it comes to the power plants and gets burned up to make electricity. So a little bit more about my group. What we do, our group is broken up into 2 different sections. There's a long-term forecasting group. They're looking out long-term. What's the next best generator to build on the system? Right now we have a portfolio of resources that's made up of nuclear, coal, oil, gas, hydro, wind, a little bit of solar. So the part of our group that's doing long-term forecasting, they're looking out at long-term projections, deciding, okay, what's the next power plant we should build? Where should it be? What type should it be? And I was thinking there was 3: location, timing, and what type. So those 3, what they should be. And we've got all sorts of options. Should it be a coal-fired plant? Should it be a gas-fired plant? Should it be another nuclear? So we're running these models and doing these projections, trying to figure out, okay, what's that right mix of resources so that we can minimize total cost. And you maybe maybe haven't taken linear algebra or anything like that, but it turns out to be sort of a big linear programming problem. You've got an objective function of trying to minimize total cost, fixed and variable, subject to a bunch of constraints. And you've got all sorts of constraints on these resources. It can, the emissions from the plant can only be a certain amount, and there's dozens and dozens of different constraints on these things that we put into this big math model. So that's one side of the business, is this long-term forecasting. The other side is short-term operations forecasting. We're looking, and that's the group that I'm in. When we look at the fuel, at this fuel portion, the group that I'm in, we try to forecast. What do we think? How much do we think we're going to spend on fuel in the coming 12 months or so? So we've got these simulation models where we're trying to simulate the operation of the grid for the next 12 to 18 months, and we're trying to figure out, okay, which plants are going to be available during what seasons, how much coal, oil, gas, and power are we going to consume to serve all of our customer demand. So that's what our group specializes in. And we've always, what we're trying to answer the question first of all is how much fuel do we think we're going to burn, how much is it going to cost. We take that cost projection and give it to the rates department. And so they divide the dollars by the volume to come up with a rate, and that's how your rate is determined for your bill. Pretty interesting, simple math. Just take dollars, divide by megawatt hours to come up with a rate. So we do this forecasting. Well, our forecast is never right. So I can honestly say that I've never done anything perfectly 100% right, because the forecast is always wrong. You're never going to get it right perfectly. If you do, then I'm probably in the wrong business. If I should be out in the stock market or something like that, if I could predict the future like that. So we spend a lot of time answering management questions. If we did a good job forecasting, then management will say, okay, great. If there's no tweaks that you need to do to make to the model right now. But if we miss the forecast by $40 million, then they come around saying, how come you missed your forecast by $40 million? We thought the fuel expense was going to be $200 million, and it came in at $240 million. So what happened? I mean, was it because your model needs tweaking, or because did the weather come in stronger than what you expected? Did the generators fail and they weren't available? Maybe a nuclear plant went offline for a while. In fact, that's a great example. I'm sure you all knew about the earthquake that happened last August. The two nuclear units at North Anna were down for part of August, September, October, and then most of November. So those nuclear plants, the nuclear resources were offline, which really is expensive. When you've got a cheap resource like that you count on to produce power every day, and it's not available, we have to replace that with other more expensive power. So we're all getting a little bit of a surprise in our power bill. It's not itemized on your power bill, but it's there. I mean, the fact that the nuclear plant was offline, and we had to buy replacement power and that cost more money. Let's see, what else? So, yeah, the two things that I'm faced with every day is, what can we do to improve our model? That's one of the main things that engineers are really interested in. Is what can I do every day to either learn something new or to make some sort of improvement to my model so I've got a better forecast. The other thing that's really interesting about my job right now is all these environmental rules. In the past, it used to be, for instance, when you look at a boiler, the goal was to make that fireball as hot as possible because you want to have real high boiler efficiency. But now it's trickier than that because the hotter that fireball is, the more emissions you can have. And our whole world is changed by the environmental regulations. You can only emit so much SO2 and NOx, and eventually there's going to be a rule for emission of carbon dioxide. So the engineers have to really work hard it's not just about making a real hot fireball in the boiler. Now you've got to control it so that that fireball in the boiler is just right, so that you're not violating any of the emission restrictions on what you're allowed to emit. Because every one of our power plants has an air permit. When you build a plant, they give you a permit and say, okay, you can build a plant, but you can't emit more than X tons of NOx and X tons of SO2 and X tons of whatever effluent that's being regulated. So that's one of the really interesting things going on right now is these environmental rules. It's changing our whole business. Going back a few years, one thing I'll say about my first job out of college was working at a company called Babcock and Wilcox. It was doing nuclear power plant maintenance. Really interesting for a kid coming out of college. At a nuclear plant, you've got the core where the nuclear reaction is happening. That's heating up the water, and so the super hot water goes to a steam generator, which converts the water to steam to run through the turbine. So the job I had at this first job out of college was working on steam generator maintenance. The steam generators are probably about 50 feet tall, and there's a round head on either side, and it's got about, I think, 5,000 or 7,000 stainless steel tubes that are 40 feet long. And what happens is when this water flows through the system, it's really high velocity, and you've got particles and junk that's within the loop that does a lot of damage to the ends of these tubes in the steam generator. So what we would do is I worked for B&W, they had these robots that would go in and repair the ends of these stainless steel tubes, because you didn't want the radioactive water on the primary side leaking over to the secondary side. You didn't want that mixing of radioactive water to clean water. So we had these robots that would go in and it would prepare the end of the tube, and then you put a plug in, because sometimes the plugs or the tubes would get worn down and you would get a leak in there, and you want to plug that tube. Sometimes you'd have to be the poor slob to go in there and set up the robot, because it's a radioactive environment inside of this steam generator. But once you got in there and set the robot up, then you jump out of the steam generator, and then everything was done remotely. Really interesting application, using robotics on how to repair these steam generators and to try to keep the efficiency high. I guess the last thing I want to say is, and I've got a boss that says this too, is you're never too old to learn something new. Don't ever think you're too smart to learn something new, and don't ever think you're high enough up in the company to learn something new. There's always, and that's what makes it fun. So if you go into work every day and find something new to learn, it really can be interesting. That's all I got. Questions?
So what was your degree in?
Mechanical
Engineering?
Yeah.
From where?
From Clarkson University. Middle school, upstate New York, about 20 miles from Canadian. Pretty cool.
Yeah.
Yeah, I mean, if you guys ever have any questions about how the grid works or how a power plant works, that's the other thing, is there's really some fantastic resources out there online, and you can go to the government websites or the Dominion website. There's different training. It's right there on screen. You can see how a power plant works, how the grid works, some of the new things that are really, really interesting. And I can honestly say 25 years later, I'm still learning new stuff. It keeps changing up. Okay. Thanks.
Thanks.
Thank you.